Welcome to the Warren seminar. So my name is Emmanuel de Tournay. It's my great pleasure to introduce our speaker today, Professor Wen-lu from the University of Maryland. Now, a few words about introducing Wen-lu. She received a PhD in 1996 from Stony Brook University, and then she moved to the Woods Hole Oceanographic Institute in Massachusetts for about 10 years. And in 2007, she joined faculty at the Department of Geology at the University of Maryland, where she's now a full professor. So she's an experimentalist. She works at the intersection of rock deformation and fluid flow, and doing very sophisticated experiments, as you will see. For work, she received a very prestigious medal from the 2020 Louis Neil Medal by the European Geoscience Union. And if I can read the citation, she was awarded that medal for exceptional contribution to understanding coupling between fluids and rock deformation, and in recognition of a role in promoting women in science and rock physics globally. She's in a very distinguished company, in particular, Professor Kolstedt, who got the same award, same medal a long time ago. No. So anyway, I look forward to your presentation. Please join me to welcome Wen-lu here.
Thank you for the very generous introduction, and thanks for inviting me here. I'm just going to talk about some of the experiments that we do in the recent years. The bulk of the work is done by two PhD students. One of them is Tiange Xin. Right now, he graduated and he's at the Massachusetts Institute of Technology working with Matei, many of you know. Another PhD student was actually, I spent a lot of time with her in Norway when I was on sabbatical, and her name is Xiaojiao Zhang, and she is now back to China and working in the Chinese Academy of Geosciences. This work will not be possible without collaboration with the Norway University of Oslo group called NURD Center. And I also collaborated with Florian Fossey, who together we started to push for doing rock deformation experiments in the synchrotron beamlines. So the talk is about reaction and the deformation, the coupling, and how does the chemomechanical feedback changes both affect the chemical reactions and changes the mechanical behaviors of rocks. And we will focus on mantle rocks, particularly mantle peridotite. And the mantle peridotite is magnesium iron silicate. And usually we don't see most of it because we live on the surface, and they are stuck to, tens of kilometers down. However, in places where the mantle peridotite actually rises up, then the temperature drops and the pressure drops. It turns out that at less than 700 Cs, peridotite becomes unstable in presence of water. Less than 500 Cs, that peridotite gets unstable in presence of CO2. So where those rocks turn up on the surface, meeting those low temperature and conditions is plate boundaries. So that's where this is a map where the three types of plate boundaries, convergence, divergence, and transform boundaries. That's where lots of tectonic activity happens, and you can lift the mantle rock up. And once that happens, so essentially, two major groups of reactions that we'll touch upon in this talk will be serpentinization, which means that you hydrate the mantle peridotite and generate a group of minerals called serpentines. And then if with also CO2 present, you generate the carbonation process. right? So listed here is absolutely not the comprehensive the chemical reaction, but some representative ones. Because we're lab rats, we often just use the end member of the peridotite. So that's the San Carlos olivine, which is having very high magnesium and a little much less iron in it. And so the reason we study this for this talk is mainly because a letter wrote to Nature, and that's the copy of that letter. This is an idea by Sifritz, basically say, hey, if we keep on using fossil oil, basically we are burning the carbon-rich materials and send the carbon from their solid state to the gas state. How about using some natural process that's making the carbonate, which can we accelerate to get the carbon from its gas state, CO2, into a solid state. So since then, in national labs supported by DOE, there's a lot of studies of different types of mantle rocks and mafic and ultramafic rocks to see what will be the chemical reactions, how feasible this can be. So one thing that everybody agreed on is these reactions tend to be exothermic. They also are solid volume increase reactions. So with that, there are out of the box thinkings of using this as a carbon storage using the mantle rocks. There are two general ways of how to use it. The ex situ ones, and this is a review paper by Power et al. Published in 2013. That's essentially you can build an industrial size mineral carbonation plant and give the mineral feed and have they capture the CO2 and then have them react and then even produce carbonate rocks that can be using as a building stones and so on. That's plan is good, but the cost is very high. And the bulk of the cost is actually not because the rock doesn't interact with the CO2 rich fluid, but because the surface area. You have to powerize the rocks to actually make it happen fast enough. But that powerization uses more power and is very costly. So you can, this is an estimate of how much it costs. The number can change a little bit, but the order of magnitude is right. And when this paper was published, that's the world's carbon total excess would be 35 gigatons. So if you think about that, to get that back, you can calculate that's really expensive. Then there's a second idea that, hey, let's not build the plants, we can do in situ mineral carbonation. Essentially, you're injecting CO2 into ultramafic mine tailings and or mafic like basalt formations. And then the question is, what would be the rate? And once you inject it, you don't see it. Do we know what's happening? So this is where this talk is motivated by. So one idea from the batch experiment and the early study is that the carbonation is probably not a very economical way to sequester carbon because it's a self-limited process, because it's depend on the supply of the fluid. But if you have a reaction that is a solid volume increase, you passivate the reactive surface or you clog the fluid pathways. Either way, you're going to reduce the rate and extent of chemical reaction. So everything becomes self-limited. So showing here, you can see this is a single olivine crystal. This is a work done by Chu in Yale when he was assistant professor there. So you see very quickly within days that the surface has generated all this magnesite. Yet after that, after 14 days, they stay there for a very long time, and you have the olivine relics in the middle. And this is actually demonstrated in some of the ODP cores that you take those rocks and these are weathered or serpentinized olivine. You see that the serpentine at the outer rim, and then you often have some of the clay minerals, but then there's always the core is still intact olivines. However, there are different way of thinking this problem. We say, wait a minute, people say, hey, it does not have to be self-limited if the volume increase reactions could produce fractures. It could break the host rock. So lots of you had experience, for example, putting fluid, a bottle of champagne. I mean, maybe not a lot of you, but some. It certainly happened to me once because you want to quickly cool the champagne, and then you forgot when the guest arrives. What's happening is it's an exothermic and volume increase chemical reaction. It's going to boom, all right? And this type of reaction happens in rocks, and lots of you actually see that the salt weathering. This happens in Maryland a lot. And my friend Adair, who graduates in Maryland, said, one thing here, people, you're amazing. You have like 3 feet of snow, everything is still open. If we have 1 inch of snow, everything closes, and the road was so oversalted that you see a lot of, concrete built environments as well as natural rocks get weathered. So this is one of the studies showing that this is a sandstone course, and with the oversaturated salt fluids consistently passing through, eventually you actually breaks that rock. So Peter Kellerman and Greg Hurst published a paper and they say, hey, those are what we call the crystallization pressure. So this crystallization pressure, they did estimate that with the carbonation of olivine, is that if you assume all that chemical reaction, the Gibbs free energy can be translated into a mechanical energy, they estimate that you can actually burst the host rock and create what they call the reaction-driven cracking. This is what I look at this as like, that sounds great. Let's look at it and see if we could do that in the lab, all right? Another thing is with the salt experiments, which Peter Kellerman often use as an example, this can happen, but most of it is at ambient pressure. So with us thinking about injecting it down to the mafic formation, we have to think about the confinement, all right? So I also don't know how this interact with the pressure. That I'm not the only one thinking about this problem. So this is the group that's in Norway I collaborate with independently. They have done the autoclave experiments. So they took a natural peridotite. This is from the Western Norway. They have lots of those rocks. They're beautiful. And then they put a CO2-rich fluid, and then they let it sit there for months, all right? So what they observe is a constant decrease of porosity. With definitely when they take they take this sample out and look at the reactions, they do see magnesite and other things, yet the porosity drops. So their conclusion is that there's no experimental evidence to see the reaction-driven fracking. And then I thought, maybe this is less simple than just an end product. Let's take a look of the intermediate step between the chemical reactions and the mechanical fracturing. And how do we do that? The intermediate step is we try to put the deformation rig, here is one of them, into the synchrotron beamlines. We do need to use a synchrotron, not just a micro CT, because we need more energy, more flux, because lots of it you need a sample environment, which is already, to build the pressure temperature, you already have quite a bit of material that is not that transparent for many of other ways. It's blocking we can't see through, even laser cannot go through very thick metals and so on. So X-ray becomes one of the means that you can go through the sample environment and see what's going on in the sample. So this is some of the technical aspect of it. So the first experiment we did was essentially we took a sintered olivine. These are olivine powders. We sinter it and built a olivine cup, and inside we put some loose olivine grains, and then let them react with 1.5 mole of NaHCO3. With that bicarbonate, and we control the pH about 8, and so this is a saline solution with carbon-rich ions. And then we let it react with the olivine sample assembly for 6 days. Every half an hour, we collect the 3D microtomography data. So here shows the timestamps, 8 hours, 65, 86, 118, and 120. This is that olivine aggregate. What we did see is at some point, these aggregates start to fracture. Another thing we see is the olivine grains in the middle actually see the cumulus. Then later on, we identified this as magnesite. So what then? We took the sample out and did the chemical analysis. You see this is one of the olivines, and you do see those magnesites, right? And those are the peaks. And but what we also see using nanotomography is what I call the etch peaks or wormholes. These are, right now, you're looking at a nanotomography, and this whole field of view is less than 50 micron. And this is one single olivine grains. And the red is actually all the voids inside that olivine grains. And we certainly didn't see that in non-reacted olivine. The one thing, this is a good angle, I will stop here. The one thing we also see is that these voids actually have these angles towards each other. They essentially forms these almost 90-degree angles. And they are studies saying that this could be an indication of the stress concentration. Once you release the dissolution channel will release the stress, and then that's why it's turned to dark the other ways. But that needs to be further investigated. So what we learned from this 6-day, what I call in situ experiments is the crystallization pressure as I originally imagined. Essentially, you put in more like a bursting a balloon, you put in a volume and there's a geometrical mismatch and then you boom, you create the fracture. That we have no evidence of that happening, all right? But what we see is that if there's you have at the surface, usually at the surface, if you have because this is an interplay between dissolution, which is the volume decreasing, and the precipitation. So if this precipitation and dissolution was somehow in making a way so that you have patches, regions of it is shrinking and the regions of it now is expanding, you could potentially develop those cracks in a fashion like the shrinkage crack. They are going layer by layer, gradually deep through. It's still a type of tensile fracturing, but not as we imagined at the beginning. But one thing that we didn't expect and which was revealed by the nanotomography are those actually the wormholes. They somehow go through like any defect inside the olivine and start to now dug holes and then they actually turns and so on. Given time, that can be reduce the strength of the host rock, make it easier to break, and but the rate of it right now we don't have because for 6 days we only each one takes the reaction takes 6 days, so then we only did 3 experiments, which it's hard to get a rate out of it, right? But we were encouraged by these results, so we say, how do we increase the rate? So I can, usually we get 2 or 3 days of beam time. We run it to 24 hours. So if I want to run 10 experiments, I want each experiment to last only 2 or 3 hours. So then we said, oh, let's not do olivine, let's just do the MgO, the periclase. MgO, hydration of MgO at a temperature above 150 C can be very fast. So what we, then the next set of experiments, what we did was we simply purchased from a ceramic company that's a periclase cores. Those has some initial porosity, which turn as a defect for them with fractures of 1 to 2%. And then we put this periclase cores and run the water through it. These are just BI water. So now the periclase, right, at temperature, the R range is 180 to 210 degrees C, because this will allow us to see the reaction complete within 2 or 3 hours. They start to, you see significant reaction once you have the temperature above 150. If you're just room temperature, it takes forever. So these are the experimental conditions, and now it's with this analog system, it allows us to actually vary the confining pressure, pore fluid pressure, stress, because we can do more. Like I said, we now do it about 20 experiments. So this is essentially what happens. So this is one of the periclase cores. At the beginning, you see these are all MgOs, and you have some defect. And now we have water, so you can start to see the water now create the chemical exchange. and then they push open it more and the reaction increases faster. Eventually, this whole core, that's more like what we envisioned as the crystallization pressure that's breaking the bridge, all right? And this type of reaction actually is also sensitive to both pressure and the temperature. Showing here is a higher temperature. It's a 30 degrees C, and we may have a spike gets a little higher, but with the temperature higher, when the reaction started, you can see suddenly the rate increases a lot, all right? And so one thing is the so during this experiment, it's done in synchrotron, and we rotate our cells so you can collect the 3D microtomography images of the whole 3D samples. With that, you get all the essentially the absorptions of each minerals, because the periclase is more absorbing than the brucite, than the void. So you can see now the color is the time at 25 minutes after the reaction, you start to see there's a peak in periclase. And as the time goes down, the periclase drops. And as the time goes pass by, the brucite goes up, and as well as the void. So this way, you can actually track those phases. If I track the phase, then this is what I see from the beginning to the end of the experiment. The green data is porosity. At the beginning, the porosity is a little less than 1% in this case. And we measure the porosity of the core before experiment. And after that, we use the imaging to track what's the growth of the porosity. You see the porosity stays more or less the same until peak. That's where the fracture started, all right? But with the peak, you have a really accelerated chemical reactions, and all the periclases, the blue is suddenly dropped to very low percent, and then the brucite is increases, all right? So that is what's going on. This really demonstrated the coupling between the mechanical fracturing and the chemical reactions. Then we were very encouraged. We say, how about, because before we have it at the 10 MPa, which is somewhere roughly 30 kilometers depth, we say, how about we increase the confinement and see if this transformation can break the thing again. So we increased it to 80 MPa. Then nothing happened. At the beginning, it's very similar. There's not much. And then we start to see only porosity decrease. And then as it decrease, it becomes essentially nothing happens. So we waited 2 hours, clearly nothing happened, then we stopped. All right. Then I said, oh, so clearly somewhere, if you increase the overburden too much, the reaction is not strong enough to push, to break the rock. The overburden was too high. How about we add some stress? Because if you put some shear in these cracks, that could help it either open or slide, or maybe that will make a change. So we add, instead of just having a very nominal end load, we added a axial differential stress. So now the sigma 1 along the axial directions increases from 10 to 20 MPa. And that actually have very similar as if we didn't have that added 10 MPa stress. So I said, oh, that must be because we didn't add enough stress, right? So I added to 100 MPa, because at 100 MPa, I calculated that some of this fracture, if they are favorably oriented, so they should start to shear and potentially grow. What I see is, as soon as I increase that, the reaction start to slow down and then stopped. I was puzzled, but then I said, okay, this is during the experiment. Because the thing start to stop, I said, let's drop this. We dropped it to 5 MPa by 5 MPa. When we dropped to 65 MPa, this thing, the reactions restarted. So clearly it's not like you put some mechanical stress on it, so the fracture can slide, helps you with opening the fluid pathways. It is the effective mean stress. All right. So now we calculate that it's roughly around 30 MPa. Whichever way you do the combination, by increasing the overburden, or even your overburden is low, you increase a deviatoric stress, or you actually could have a high overburden and increase the pore fluid pressure. As long as the effective stress is below 30 MPa, we can fracture the periclase. Once you go above that, we can't. I don't have answers why 30 MPa, but I think that's an important thing to think about. So my collaborator, Bjorn Janvet, and he says, oh, I know, I published a paper and we talk about, this crystallization pressure and the fluid-assisted chemical reaction, because, between the periclase and brucite, to have the reaction ongoing, you must have a water film. But this water film is repulsive, so that if your overburden is too high, you can actually squeeze that out. That's the disjoining pressure, which is actually, at least when I started this, I don't know about that, and I didn't think about the crystallization pressure would be related to the disjoining pressure. But that is one of the thinking. I'm not sure this is right yet. I'm just putting it out so that you may help me to decide that. I am still from a rock deformation point of view, I thought, but maybe this is the brittle ductile transition type of deformation. I can imagine the brucite at a certain rate, if you deform it very slow, instead of breaking rocks, they could start to flow. So the creep of the brucite might be also another reason. I don't know. I want to look into that hopefully later this year. So one thing though, I find is really interesting, because I have been looking at the pore fluid pressure. How does that affect the fracture pattern independently from this study? So if I do my comparison of the 10 MPa overburden, 5 MPa fluid pressure versus 80 MPa confinement, and 75 fluid pressure. So both of them have effective stress of 5 MPa. Both, as I said, we find that below 30 MPa, this chemical reaction can produce fracturing. Both actually fractured. However, so what you see is this is our confining jacket. This is the periclase core. and that's the initial fractures. And this is after a few hours, 2 hours of reaction, right? Essentially, you break this down. And this is low pore pressure. This is high pore pressure. You see, this one has a big relics. The fracture, basically the fracture, single one of them are longer. They are fewer. This one, the fracture are much more numerous and shorter. And because they are much more numerous and shorter, you create a lot more surface area. That's why this is almost 100% complete chemical reactions, whereas that has the relics. I think that's really interesting. So to summarize what we have, that this is among others, some of them are, you see the numbers, some of them are repeat, some of them are failed experiments, and unfortunately we all have failed experiments. And but essentially, what we summarize is one thing: the primary control of whether the chemical reaction can proceed to completion is the first order depends on the effective overburden. That's the overburden minus the pore pressure. Second is that the rate of the brucite growth seem to correlate with the temperature. Higher temperature certainly make it faster, and correlate with pore pressure. With higher pore pressure, you're having it slower but more complete. So that makes it, I thought, wow, I told Xiaojiao that for the last chapter of your thesis, what you really should do is we should put this periclase core into a peridotite. So outside is a peridotite from Western Norway, and then we drill a hole and we put the periclase core. And when the periclase is not increasing, we want to see how much stress it can generate to break the host peridotite. All right, and move. So now what you see is this is the confined jacket, the dark gray, and that is a natural peridotite, and this is the periclase core, and that's the initial fractures, and we have DI water running through. And on the left is a low pressure, pore pressure one. On the right is a high pore pressure. So this is pore pressure of 5 MPa, that's a pore pressure of 75 MPa. And this is so to keep the effective stress the same, this confinement is 10 MPa, and that's 80 MPa. And what you see is as this core gets expanded, they do create enough stress to break the host rock. But in the low pore pressure ones, you have incomplete reactions and fewer cracks. In the high pore pressure ones, you have rather complete reactions and very many numerous cracks. So we also looked at the rate of the growth, and the low pore pressure ones is growth faster, but then it also stops. Whereas the high pore pressure ones, the rate was slower, but it's more complete. And we repeated this, and this is what we see, the fracture densities, which is average in the different levels, and you count those cracks. And in general, what we see is a positive correlation between the pore pressure and the fracture density. That can have some implications of how mechanically we can do this. So then with this, now working with Jessica Macbeck, she has done this string analysis using digital volume correlation. Now we have a time-resolved series of microtomography images that she can take cubes of those and tracking individual grains and see how they change. And that's you can get a full string tensor field of those samples. And from there, she actually can analyze this, where the porosity, where the brucite, where the periclase, and what types of cracks that you're braining the string, the dilation versus shear versus the compactions. I think that this way we can start to really see this coupled environments, what type of mechanical impact or load you are giving to the sample. This is also ongoing. So to summarize, I think we did a series of experiments, and they revealed quite a few interesting things that we learned before that I wouldn't know this. But there are also, like many researchers, it opens up many more questions. Hopefully, the thing we learn is now the question is more pointed. And so I just want to summarize to say that this new way of conducting these experiments can be really important, especially when you are thinking of a coupling system. And right now, we're using the dynamic synchrotron microtomography to study those systems. In the two examples I gave, that's because of the added dimension of time, the intermediate steps, we can see in real time the growth of new phases, the dissolution development, and how the geometrical pattern emerges, and as well as the strain field. So I am hoping now is my plug that you guys would be interested to think about taking your study and looking at, because this morning I visited the rock mechanics lab here, and I'm sure there are other labs that maybe we should, as researchers who are interested in this coupled system, to look into the new ways, the new experimental methodologies to study this process. And one of the things that we are currently have is an NSF-funded research coordination network. Actually, Lars is the steering member, and Dave was my advisory members. And what we want to do is basically for people who are interested in the dynamic process of geomaterials to think about adding a dimension by the time into their experiments, and then learn more about what's going on and the feedback mechanisms. So our next networking event is a science workshop. This is jointly hosted by University of Maryland and the NIST. It's going to be exploring the dynamic property of materials using neutron technology. So far, what I have here is all X-ray synchrotron. Neutron actually have even more power to penetrate heavy metals. And if you go to higher pressure and the temperature, need the sample field environment much heavier. Sometimes the X-ray has its limits. So we like to explore what's going to happen in the neutron technology. And this workshop will be in July 25th to 27th. And depend on how many participants we provide support. And with that, I welcome questions.
Thank you for sharing those very exciting experimental results. They are really thought-provoking, and I'm sure that we are going to think about them for quite some time. Anyway, the floor is open to questions.
Yeah, thank you for your talk. I was wondering about your hydration experiment. When you increase the deviatoric stress, you stop the reaction, right? Or
Above a certain
process.
level, yes.
Is it possible that by having high deviatoric stress that you're opening some of the fractures, that your advection rate becomes too fast for the reaction rate?
I didn't see that. The reason I say that, that's certainly a question it never occurred to me that the thing would open too fast. The reason is when we see this particular example, right? And this opening, that once it opens, this particular one, because the temperature is really high and overburden is low, it opens really fast. So what we have seen is half of the sample essentially interact so fast that they split. All right. So if what you said happens, we should see in our image at least in a region that you have a sudden change.
I was thinking about the number 6, right? When you
Number 4 is
really high axial stress and nothing happens, right?
yes. This is the high stress.
I was thinking
So
about that one, that
we have
fractures are being open, the pre-existing ones are being open, and
right.
hydraulic conductivity increases.
If the pre-existing one happens, so we actually do trace them. We try to look for it, right? And I would, with what you said happened, I was expecting then this place is actually gets replaced. Then maybe what we see is these are typical ones. So what you see is you have the replacement in the crack, but they just stay there. So it's really more infill. Obviously, we didn't trace every crack, but the major ones, you actually pick them out and look at it. Every single ones that if they're bigger, you can see that they are brucite infilling it rather than, like you said, they are too fast, and so that's yeah.
Question on this. So the axial stress is very high here, but the so-called confining stress is very high. So the deviator here is small. So I was wondering in this particular experiment, if you have an effect of mean stress and permeability. Yeah, this is a different one.
This one, okay, I got confused that this one, the actual stress, this is just an unload of 1 MPa to prevent the having a tension, right? So this is mostly the increase of the overburden. This is the confinement is very low, and then we increase the that, and once we start to increase it again, we just stop it, and then you can see the infilling there. But you decrease it. All we did was, okay, it doesn't do anything anymore, but I don't want to abort this experiment. So we decrease the stress, and then suddenly things start again. So I do believe that at least for now, all the experimental evidence is that when its overburden is high, the brucite obviously first increases at the wall of those cracks. Then if the pressure is high, they just infill this and then block it and stop. But when the effective stress drops, then they start to be able to push and open. So I definitely can see there could be also a rate in it, like how fast you can do this. That's why I'm also thinking about the brittle ductile transition. I'm thinking adding how fast you're adding this, and that's could, you know, the crystallization stress or pressure, how fast you push is playing a role.
Thanks for a really interesting talk. I wondered with the periclase and brucite system, if you know enough about the different pressures and their effect and the chemical reaction rate, if you can then extrapolate that to the periclase system, or not the periclase system, the olivine system with CO2, and design an experiment that you could run to test whether it's the same governing principles based on what you know about that reaction rate. If you could, you know, tweak the temperature, tweak the pressures so that you can see, does that system behave the same?
That is the whole,
Okay.
but it's the difficulty comes from the brucite, well, any of these chemical reactions. The better constrained rate is almost always come from powdered experiment. And so once the reaction needs to create its own pathways and own new reactive surface area, that is become unknown. So that's why we feel that this opens one way, at least we couple that in. So because that's mechanical feedback is really hard. Because I think the chemists, they know the rate, but their rate is always based on the powder experiment. So everything is granular to the best, like, you know, larger grain size versus smaller grain size, but they have almost infinite surface area to play with. Whereas if you are looking at a rock, you have limited to start with. So the key control again becomes whether you can keep or increase the reactive surface area. And that is the mechanical part, which I think it's a harder problem to answer right now. But that's the hope. To first use analog ones faster enough so we can just do as many as we want and get to some rate or kinetic laws. And then hopefully to say, oh, mechanical strength is similar, chemical reaction rates, and then do some, you know, more modeling to try to predict. But that's exactly what this is about.
Thanks. That was a really cool talk. You kind of foreshadowed this a little bit. Do you have any ideas or as to how to test the disjoining pressure hypothesis for those cracks opening? Do you have any experiments in mind?
Part of the reason I come here is because I went to a conference, I talked to Peter Kahn, and he has some really cool experiments looking at the you know, the chemical reactions at the surface, like the mineral surface. So I'm hoping that someone who actually study those would be able to help because from the pure, I'm much more a mechanical experimentalist. So from our part, it's getting hard to really getting there. And unfortunately, right now with the atomic force device, it's very hard to keep any confinement there. They can start to do some temperature, but putting the confinements, even the nominal one, seem to be still very challenging. But maybe you can think about it.
I just wonder if you're able to see in the low pore fluid pressure experiments, if there's like reaction products being transported long distances.
No, we haven't checked the actually any of the fluids chemistry, if that's what you're asking about. That's definitely something to think about.
Thank you for the interesting talk. My question may be a little bit different because I'm outsider. So I noticed the temperature are quite different from case by case. I just wondering whether it's by design on purpose on what general effect of the thermal on the chemical reaction and the mechanical stress.
Yes, that's a very good question. So as I'm not a chemist, and so this is why this is a periclase 1, and that has the highest temperature. So my understanding is if we increase the temperature, things will go fast, right? That's why the first one, because our rate was rated to 220. Because after that, some of the seals, pressure seals can break down. So I said, let's go for 210, because that's the highest we can get. So that's, I'm hoping this will definitely give us some reactions and it will be fast enough where I don't have to wait for 3 days to see the product. And then this is what we see, it's kind of fast. Within 2 hours, everything reacted. Then we say, okay, we can breathe and let's drop it to 180. So if you look at it afterwards, because you do not want to push, even though the seal did not break, but they need to be replaced very soon because they lose their elasticity and everything. So after that, we actually have it mostly below 200.
Thanks. Thanks, Wen-lu. That was a really great talk. So I am, like a lot of other people, I'm interested in the kinetics of this, of what you're showing. And so, but also this link to the brittle ductile transition. So one way you're exploring the brittle ductile transition here is by changing the mean stress. But the other way to do it is by changing the temperature, right? So as you increase the temperature, you're going to increase the reaction kinetics, the reaction rate. But you're also going to increase the creep rate, I guess, of your initial phase. So do you predict that as you go to high temperatures, you shut things down because the initial phase is too ductile?
I don't predict anything. My plan is to actually drop this to 150 and see first if the apparent threshold moves, because that's, I think, is durable. It will last not 3 hours, but more 5 hours. But because I need only 3 experiments, that's my first plan. you know the ductile fields much more than I do, but if you have, ways to, change the loading rate or something, I am out ears. But yes, in September, the first 3 experiments we want to do would be drop it to all at 150 and see if the required threshold moves.
Especially because it's going to depend on an activation.
Yes.
It's going to depend on an activation energy for the reaction and then the activation energy for the creep. Yeah. So there's a funny non-dimensional number in there.
That's right. That's absolutely right. Yeah. But if you can help thinking about it, see, that will be great. One person can only do so much. Yes. David.
Is there anything in the literature about the plastic properties, geological properties of brucite?
The only thing, David was asking if there's literature talking about the plasticity or the rheology behavior of brucite. The only literature that we find that has some systematic study is from Diane Moore. She has an early study that's having brucite as one of the gouge materials they actually looked into.
Yeah, thank you for the great talk. I have a question about the experiment that mean stress was very high. So you didn't see any fracture in that experiment, but you said that you saw some replacement in that experiment, right?
At the beginning.
Yeah. So what did you think about it? What happened if you let the experiment run a little last longer than 180 minutes? You won't see any crack or something if the experiment run a little longer than that.
We basically, for the one that stopped reacting after a few tens of minutes, like 20 minutes after, you don't see much, right? Because we waited and it doesn't seem to do anything, we just dropped it. This definitely doesn't say that if you can wait for a month, if something would happen. That I don't know, I cannot just say. But in terms of the crystallization pressure we are looking at, I think I, at this point, lean to that the longer you wait, the less possible that you can actually create enough crystallization pressure. But on the other hand, a lot of these things has a dissolution going on. So that dissolution, because it's always the interplay between the precipitation and the dissolution, that dissolution could, at a longer time scale, which is not addressed in those experiments, do something to the system.
So before we close, I'd like to ask a question. You showed that, first of all, the importance of the stress, how the reaction is going to be controlled in a sense by the stresses. At the same time, in order to have self-sustaining reaction, we have creation of surface, therefore dilation volume.
Yeah.
Now, all those experiments are done under controlled stress. Now, if we start to think about the field, we have confinement, we have elastic confinement. Can you maybe think about what would be the implication of that in terms of the fact that you dilate and therefore you are going to increase the stress, the confining pressure? What would that do on the sustainability of the reaction?
It's everything. It really depends on also what is the surroundings, right? Because as you generate, that's why we did these autocorrelations to try to analyze the strain field. There are places that's dilating. There are places compacting or shear. I think that's probably is the way, or what I can see, the only way to say something more experimentally supported to address these questions. But that's again, right now, we just started in the sense of you have a mine of this data, and what else you can look into to try to predict the rate and so on. So looking at the evolution of the stress field, the strain field, and then using that to infer some stress seems to be a way to move forward.
All right, I think that's we have to ask this question. Show the interest that we all have about your seminars. So please join me to thank you again.